will become available sometime soon. So I think with that, folks, it may be time that we get started. This seminar, takes place every Friday at noon Eastern Time and is dedicated to you, the research and academic communities. You can stay up to date by subscribing and hear the latest talks that are coming up. Today, I have a very special pleasure to host here Professor Sabre from Purdue University, who will talk about quantum machine learning of complex systems. And hello, how are you today?
Hi, thank you, Zlatko.
It's good to see you. And we can turn your camera on at this point if you'd like. Hello, where are you tuning in from today?
Yeah, I'm in my office at Purdue University in the chemistry department.
Well, we're delighted you could join us. Allow me to give a bit of background to your long and distinguished career before we get to your slides. Sabre received his bachelor, master's, and PhD degrees from the Hebrew University of Jerusalem in 83, 84, and 89, respectively. He went on to a research associate at Harvard University in the Department of Chemistry, and since then joined Purdue University in 1994 as a assistant professor of theoretical chemistry, and he's now a full professor of chemical physics, computer science, and physics. So quite a broad spectrum of things, and very impressive to unite all those together. Sabre was the director of the NSF-funded Center of Innovation on Quantum Information for Quantum Chemistry, and he is a very distinguished man, a fellow of the American Physics Society, American Association for the Advancement of Science, Guggenheim Fellow, Purdue University Faculty Scholar, and the list is long. I think you get the picture. So with that, it's our pleasure to have you. Folks, you can ask questions live during the talk, and we'll try to get those up to you. And otherwise, the stage is yours.
This is. Oh, thank you so much, Zlatko, for the introduction, and thank you for having me on this important series of lectures on Qiskit. And also would like to thank all the people that are tuning in from all over the world to participate in this seminar. And I also would like to take this opportunity to thank IBM for making their machines and the Qiskit available for the whole community all over the place. And today I'm going to talk about quantum machine learning for complex chemical systems. And before doing that, let me just give you the outline so you can see where I'm going with this lecture. First, I'm going to give a brief introduction to the research. Just get this one here. Oh, sorry. So I'll give a brief introduction to our research and what we do in the group. And then I will focus on machine learning. And you will see the problem is to do electronic structure calculations of molecules and materials. And the model that I will be using is the restricted boson machine. I'm trying to get this one larger here. And then I will introduce the quantum algorithm and explain where the quantum part comes into this model and why we have a speed up in the calculations. And then we'll talk about the quantum circuit that do the sampling, and then implemented on IBM Qiskit and IBM quantum machine. And then we'll show results from this on simple molecular system like H2, lithium hydride, water, and then 2D materials. And here we'll show examples from hydrogen, from hexagonal boron nitride, graphene, rubidium disulfide, and tungsten disulfide here. And then we'll show application in a different area, like in a quantum phase transition, how to use a quantum machine learning to identify different phases. And for that, we'll show results for the quantum Rabi model. And toward the end, I will end with the future work outlook, what we do in the group, and how we're going to push quantum machine learning in different directions. And I will just mention how quantum machine learning can be integrated with open dynamics, quantum tomography, quantum thermodynamics, optimization, and now we have also project with engineering, how to do inverse design engineering problems. So before doing that, let me just go through the what we do in the group. So we started about 20 years ago, and the focus at that time was on entanglement and chemical reaction. I put here the picture of my first graduate student, Zhen Huang, who did his PhD with me in 2002. And the idea was to really quantify and examine entanglement and the relation of entanglement to electron correlations, and how do you examine and quantify entanglement in chemical reactions. And then we went through the research of quantum coherence and the role of quantum coherence in complex chemical systems. Like, what is the role of coherence in transport? For example, when you talk about dynamics of exciton materials and photosynthesis, or how birds finding their magnetic north, does the coherence entanglement play any role? And then we went into the idea of using or developing quantum algorithm for electronic structure calculations. And this is the focus of the talk today. And I will also mention here the idea of using finite size scaling to predict and detect criticality, and not in the thermodynamic limit where we are used to, you take the number of particles to infinity. I'm going to map it to the qubit space or Hilbert space and show that also we can talk about criticality in Hilbert space. And then we have project on data analytics and quantum machine learning. And there are two projects here in the group has to do with the stability of the grid and solar farm optimizations, as the number of parameters is really huge. I mean, you talk about 10 to the 15 and so, and it's really hard to manipulate these data with the classical machine learning. And we have also a couple of projects on open dynamics and noise and how you describe quantum master equation and run it on a quantum computer. And of course, also related to noise, we can also have, we talk about quantum encryption protocols. And at the end, I would like to mention that also we were involved in educational program using the quantum tic-tac-toe. Instead of having one move in classical system, you have two moves at the same time. And the idea was to teach our freshman chemistry and illustrate the concepts, what is quantum coherence, superposition, entanglement, and collapse when you do measurements. And we thought this is really a nice way to introduce this concept to the freshman chemist. Now, all our papers are on the archive, and you can find all the published results on our website. So let me thank right away the group that doing all this hard work. And we are lucky to have talented students from chemistry, physics, computer science, and recently we start having students from electrical and computer engineering. And I will mention their specific work and role as we go on in the lecture. So when we talk about electronic structure on a quantum computer, you can divide the work into three categories. One is the early work, and still people are really developing algorithm using the gate model. And we started with the phase estimation, direct methods, and many development in this field. And recently we start seeing the hybrid, the classical and the quantum, like VQE and other algorithms. And this is not only in the qubit space, qubit, and I will show results also in qubit space. The other category, you can see development of quantum algorithm for electronic structure in the adiabatic model platform. And the idea was here to use, for example, gadget theory or transforming k-local into 2-local. So in the early days, we use it to simulate it on a D-wave where we have an Isaac type Hamiltonian. But also people are pushing this into quantum simulators with analog simulation. And the third category, you can see that the new development in quantum machine learning, which is the idea of combining classical machine learning with the quantum algorithms to speed up the calculation for electronic structure calculations. And here I will focus on the restricted Boltzmann machine. Just to remind you, remind the new students here in the audience, the early work was built on the phase estimation algorithm. This was introduced in '95 by Alexei Katiev, and we used the paper of Seth Lloyd in the physical review letter. He has the reference here. And the idea, you have two registers, you do superposition, and you do like up to this point, it's equivalent to quantum Fourier transform. And then you do the inverse to measure the phases. So the idea for a given unitary operator, unitary, which is given here by the exponential of the Hamiltonian, which is now that you can see the phases is the energy. You can diagonalize this U and get the phases, which is here in terms of phase shift here. And there is a exponential speed up in this one compared with exact diagonalization. Of course, in the pioneering paper by Alan, Peter Love, and their co-workers, they put together the first paper in Science back in 2005 using the phase estimation algorithm to show that one can do the simulation for molecular systems. At the same time, my second graduate student, Hifeng Wang, who did with us his Ph.D. in 2004 and 2008, he did his master in abelian method with Mark Hoffman and came to my group to work on developing quantum algorithms to map these methods into a quantum algorithm and do quantum simulation for these abelian methods. And we end up with using the reference as the multi-configuration self-consistent field method wave function to get the excited states. And this was publication back in 2008. Again, after this introduction, I will stop if there's any questions. And then back in 2010 or 11, with a new student from computer science, Anmar Daskin, well, he's graduated from the group, and he's now a professor in computer science at Istanbul Media University in Turkey. And at that time, the focus was on quantum circuit design for a specific molecular system. And you can see here in this diagram with the quantum circuit for H2, what we did in his research, he was optimizing the parameter in the rotational gates. We did not call it this fancy name, hybrid classical quantum at that time, but we said the quantum design of these quantum circuits. And the cost function, what we're optimizing is the distance between the unitary matrix that you optimize in relation with the exact unitary matrix. So this was cost function, but we were optimizing the rotational gates or the rotational parameters, the rotational angles in these rotational gates to minimize the distance between your approximate circuit for that particular U in a basis set and the exact one. And we have these results back in 2012 showing how do you do simulate H2 or water system or simple molecular system. And this will take us in this introduction to 2010, where we put together this reference book in advances in chemical physics. We have 17 chapters from many groups in the field. And this collection of chapters came out of the center, and this was the first NSF supported center CCI, which is the Center for Chemical Innovation. And the focus was the whole center on quantum information for quantum chemistry. And of course, I mean, we did it with my colleagues. And here you can see in this picture, so I have a noisy picture like what we have a noisy computer now. But you can see from the left, we have Ken Brown, now at Duke, Peter Love at Tufts University, myself, you have Alan, you have Danielle Lidar, and then Alan Asperguzek, who is in Toronto. And a couple of reports still in our website, if you'd like to look at the summary, what we achieved back in 2010 to 2013. So here, let me mention also a couple of references, not review articles in quantum chemistry and quantum computing, for those who would like to see, because I'm not going to discuss how do you map Hamiltonian to qubit space. I will use these are now a simple procedure, which is already documented in so many papers, and move on to focus on quantum machine learning. And the first review article here by the first author is Yu Dong. He did his PhD with us back in 2012 and did a postdoc with Alan Asperguzek at Harvard. And he is now a leading scientist at the Zapata Computing. So these references really summarize the field, and I mean, you can see the dates, 19, 20, and this is from last year. These came up from a workshop that organized by NSF and other agencies. So you can, if you are in the field, you can ask, okay, so what did we achieve so far? I mean, what do we have? I mean, at this point, is really, you can think about it as we have a proof of concepts, like the early days of using classical computer for solving chemistry problems. We have simple molecular system, like from 2 up to 12 qubits. We went from H2 to H hydrogen chain of 12 hydrogen atoms. But what is important also, all these systems already implemented on all different types of platform, from D-Wave, an optical quantum computer in the early days, NMR, and recently with trapped ions and superconducting qubits. So we have a proof of concept both in the algorithm and in the hardware that this works. And the question is, what is next? Because people are in this field said they're getting tired because every time you have a new algorithm, you see how it works for H2. And the question is, what is next in this field? So when you talk what is next, I mean, you have the hardware and the software. In the hardware, I mean, we talk about what IBM defined as the quantum volume problem. So you'd like to increase the number of qubits, circuit width, circuit depth. Here we talk about shallow quantum circuits, and this is related to the coherence time with the system, the architecture and connectivity of the qubits in the system, and of course, quantum error corrections, and the ultimate goal that everybody is looking for in the future is having a fault-tolerant quantum computer. So this is in the hardware, and on the software, we said, okay, improvement of the hardware alone is not really enough. Can we come up with or design more efficient programmable quantum circuits for molecular Hamiltonians? And if you look at the literature or the work in this field, you see it takes many directions. One very popular is the hybrid classical and quantum, like VQE and other algorithms. The second category of algorithm has to do with adiabatic quantum algorithm or adiabatic quantum computing. And today I will focus on the quantum machine learning and talk about only specific model in this big field of how to combine a quantum algorithm with classical machine learning. And there is another development. Instead of working with the qubit space, can we work with the qubit space? And this is in relation to the advancement in the photonic quantum computing. And of course, the programmable quantum simulator that we see many groups developing these nice simulator and large really number of, I mean, if we look at the optical lattice, there's large number of degrees of freedom that can be simulated here. So in the form of phase estimation for qubits with the graduate student Yuchen Wang and my postdoc Andrew Hu, we show how one can generalize the phase estimation algorithm from a qubit to qubit space. And this was a collaboration project with the engineering group here at ECE at Purdue, led by Professor Andrew Weiner, where they did the experiment and we show how qubits, I mean, they work with the time frequency qubits here, and then we show how one can do diagonalization of a simple matrix like 3 by 3. And the results were published in Advanced Quantum Technology back in 2019 with all the details. And then we decided to write a review article with the help of our friend Barry Sanders from Calgary that put together a summary of what people have done in this field. How do you generalize quantum circuits from qubit to qubit? How do you do the qubit Fourier transform? How do you do quantum phase estimation algorithm in the qubit space? And this published in Frontier in Physics with the title Qubits and High Dimensional Quantum Computing. So I encourage, if you would like to look how one can do algorithm in the qubits, maybe you can see what we have done, what people have done in this field. And another development which is really important in our group was how to map the Schrödinger equation to Ising type Hamiltonian and connect the two fields that when we teach classical mechanics, we teach the Ising model and all the development for the last 100 years. And when we do quantum, we start with the Schrödinger equation and we talk about it for the last 100 years. And what will be interesting for us was to see if we can connect these two fields. And the transformation is published in this journal Physical Chemistry back in 2018. And the idea is really to increase the space. So you add ancilla qubit and you increase your space, and there is an exact transformation which allows you to increase the space and move from the Schrödinger equation to Ising type Hamiltonian. Although the transformation at the end, it turns out to be not efficient, there is an exponential cost when you include more ancilla qubit to do the transformation. But the real exciting part is not really getting the ground state energy from the Ising Hamiltonian, which is an approximation with this transformation. The idea was really to look at what is the equivalent of phase transitions in the Ising, because in the Ising model, you see the rich phase diagram. And it's really important to see if there is analogy of these phases or the symmetry breaking in electronic structure configurations. And this is exciting because about 20 years ago, we were examining criticality in chemical system. And we argue like ionization when the electron leaves the atom, or you have dissociation of the molecular system. There is a beautiful critical phenomena underlying all these processes, and we calculate the critical points and critical exponent. And now back to this transformation, we try to really connect the two. When you map your Hamiltonian to qubit space, do the transformation with ancilla qubit, and connect with the symmetry breaking of electronic structure configuration, and then see if we can explain what we found earlier and as this critical phenomena in electronic structure calculations. So this is the introduction. So maybe I will stop here if there are any questions.
Hi, folks. Feel free to post the questions in the chat. Meanwhile, I think there is a quick question from Nalay here. Is there a limitation to the value of D based on currently available physical manifestations? I guess that one might be more for me, but if you'd like to take that one. I think he means the value of D in this extension to D-dimensional qubits.
This one? You talk about the qubits in the estimation. This one is the question about the qubit in D-dimension. So for this one, I mean, the experimental group were able to do 3 by 3 simple matrices, and now they are moving to 4 by 4. So at this stage, it's really in the simple matrices. So this is what the experimentalists can do now. They're doing 4 by 4 matrices with using the 4 distinguish frequencies.
Gotcha. And maybe this might be a very small question, but in the formulation of the Z matrix, it's 2 pi I over D. I think sometimes I've seen that maybe there's a pi I over D. Does that work as well? Do you have some intuition on that? Or
You mean here?
Yeah.
I mean, when we generalize, this is the way we generalize it, the Z gate in D dimension.
Mhm.
So you are saying like we can generalize without the 2, yeah?
Uh, yeah, maybe this is a side thought because you can form like the generalized poly group with signs and phases or without, but maybe that's a fun discussion to leave for the end. It's a little too nitty gritty here, so I think let's let you proceed for now.
Okay, so now let's proceed to the main thing, which is the quantum machine learning. And with the quantum machine learning, I mean, if you look at this field, you have so many work in this field for the quantum principle, component analysis, quantum support, vector machine, and so on. The list goes on. I mean, you have many groups, many people working in this field. And I recommend this review article was published in Nature back in 2017. And this is a quick review of the field up to 2017. What I'm going to do today, I will focus only on deep learning and artificial network and use the model of the restricted Boltzmann machine. So this is our focus on quantum machine learning. And the goal is, of course, to do electronic structure calculations. So if you look at the field of machine learning, it's everywhere. It's like it's in solar farm optimization, drug discovery space, grid stability finance, self-driving cars. And here I just put the self-driving meal machines at Purdue, and here has our president receiving his lunch. So it's everywhere. So what is in common of all of this machine learning and solving different problems? I mean, if you think about it, it's like really we have two things here. You'd like to reduce the dimension of the problem. You have a large number of data. Like in the grid stability and solar farm, we talk about 10 to the 15 points. So you'd like to reduce it and extract useful information about the system as accurate as you can. I mean, this is the summary of the whole field. And this is why we went to quantum machine learning. And you will see in a minute how this is going to help us in solving the many-body problem. We are focusing on solving the many-body problem and how do you describe the wave function. So we are combining machine learning with the quantum algorithm. And here, just to clarify, I see all other people saying quantum machine learning, and they mean using classical machine learning to solve quantum problems, like, for example, finding the best density functional exchange correlation functional, or solving the Schrödinger equation or ab initio method. So here we are not really using classical machine learning to analyze quantum problems. Here we're combining quantum algorithms with classical machine learning, and we talk about quantum machine learning, which is a little bit different from using classical machine learning for quantum problems. So the inspiring paper in this field was published by Carello and Troyer back in Science in 2017. And they analyze, can we use artificial neural network to obtain the wave function for many-body system? So what is the challenge here? I mean, the challenge is how to describe the non-trivial correlation encoded in the exponential complexity of the many-body wave function. So you have large degrees of freedom, you have exponential complexity, and as we mentioned in other problems, you have large dimension of Hilbert space. And we're asking the same questions. I mean, if you look at wave function representing many physical problem, you can describe or categorize this by really smaller amount of information, and you don't have to go to the whole full Hilbert space. So you see the motivation is the same. I have large number of degrees of freedom. I would like to reduce the space, and again, use machine learning tricks to extract useful information. And here we talk about useful information about the wave function. And this is exactly the idea was put back in the science paper, how to come up with machine learning algorithm which will extract the wave function. So here is the focus on I will talk about the Boltzmann machine. You have two layers, input and output. You have a visible and hidden layer, and this is the output. And the output, of course, here would like to get the wave function. And if you know the wave function of the system, you know everything about the system. And this was the article in Science. And they show how the restricted Boltzmann machine can obtain the wave function. And they show examples of the transverse field of Ising in 1 and 2 dimension, and the same with the Heisenberg model, and show very good accuracy with milli-electron volts. Now, for us, what is the excitement? Why Boltzmann machine? And I will talk about it in a minute. In this here, I borrowed this slide in the middle from Professor Spiro Data here at Purdue, where he teach a course in Boltzmann law, physics to computers, and explain the physics behind Boltzmann law, machine learning, and quantum computing. And I thought this is really exciting because we merged the three fields: neural network or machine learning, what people have advanced in this field, the quantum computing. And it's really important to really map it to or try to combine it with the statistical physics that we have knowledge of this Boltzmann law and for many, many years. And the idea is really to get deeper into the method and try to explain the physics, because here the Boltzmann distribution is exponential with the energy over kT, and K is Boltzmann factor and T is the temperature. So you see the idea is merging three interesting fields: neural network, statistical physics of Boltzmann law, and quantum computing. And you will see we're going to build a quantum circuit that do this sampling. And when you look at the history, I think people trace back the restricted Boltzmann machine to the work of Paul Somlansky, and he's in computer science at Johns Hopkins back in his paper in '87. And of course, the pioneering work of Hinton. And you can see the reference here from 2006. So people already use this in classical machine learning for 20, 30 years. So let's define the problem. What's the problem that we are solving here? The problem is we have a system. You write your Hamiltonian. The Hamiltonian is a matrix in d-dimensional space. And the idea is to write this eigenvalue problem and find the wave function which represents the system, which is the eigenvalue of this Hamiltonian. And this will give you the whole spectrum. And we are not only looking at the ground state, we're looking at the whole spectrum, ground and excited state. And you'll see in materials, we look at the conduction, we look at the valence and conduction bands in this material. So with our approach here, we shall construct a neural network to learn the required state of the system, construct a quantum circuit to train the network, and implement the machine learning on a quantum computer. So if you missed details about what I'm going to describe now, the talk now will focus on three papers. Two already published. The one back in 2018 in Nature Communication was a quantum machine learning for electronic structure calculation and simply for molecular system. And then we generalize it to periodic system. And here the contribution, I will mention also the Japanese group. They took our algorithm and they show how to do it for periodic system. Our contribution here that we built the circuit and we implemented on a IBM Qiskit and a quantum computer. And then the third paper, this was only for the ground state. And here, this one, which is, you can find it in the archive, for getting the whole spectrum, valence and conduction band, and looking for excited states. And here I will mention specifically the students that are working on the project here. I will start first with the work of our postdoc, Manas Sajan, who really leading this effort, and Shri Hari from electrical computer engineering. And the first work back in 2017 and 18 was done by Rongshen, who graduated from the group last year and went to work with the Facebook. So before going to the details, let me just give you what to expect. What I will show you at the end. We'll construct the 3-layer restricted Boltzmann machine to train the system, and training meaning here get the wave function. We'll implement it on a quantum device and show that the resources are quadratic, which means the scaling goes quadratically with the number of qubits, the circuit width, the circuit depth, number of gates, and the parameters that you optimize in the restricted Boltzmann machine. And here, if you compare with the classical, I mean, it's exponential. And I will come back to this one. And you can see, okay, what about the sampling? You have to go to successful sampling. What we will do in here we show that there is a lower bound for successful sampling, and we show this is analytically, and we have this proof in the paper. And then we implemented on 2D materials. And when we implement it, it's not only classical simulator, and we use Qiskit and also the real IBM machine, and we show results with high accuracy. And when we talk about accuracy here, we talk about chemical accuracy, which is 10 to the -3 or 10 to the -4, or in the millihartz accuracy. And at the end, we'll show except the agreement. Except the agreement means these are small size systems and a proof of concept, so we compare with the exact diagonalization. So let me get to the
maybe a quick small question on clarification, just so we use the same term. When we say circuit depth, if you have 2 single qubit gates, one after another, is that considered depth 1 or depth 2 in this case?
Yeah, I'll come back. I will explain it. I will show the circuit and then I will show it. So all right. It's sequential gates. So for example, if I have control, you'll see control a qubit. This will be 6 times the decomposition. Because we have single qubit. I will show you, we have in the circuit, we have single qubit and 3 qubit gates. You have to decompose it. So let me, I will show you, because I mean, in this one, if I look at the visible and the hidden pair, and then you have the ancilla, which will be the product of. So when we talk about the scaling quadratic, we'll talk about the number of qubits in the hidden and the visible and the ancilla qubit. I will show the quantum circuit so you can see exactly what I'm talking about, the resources. So you see here that we have a hidden and visible layer. And again, the wave function is sampled from the visible, but there is a bias on the visible and the hidden layer. And this is the matrix or the connectivity between the 2 layers. And of course, restricted, there is no connection in the visible or in the hidden. And we have phase nodes, and this is a complex. We have the real part and the imaginary part, and these are directly connected with the visible layer. And you see here, this is the nonlinear function, which is the tangent hyperbole of this complex phase. And at the end, you sample the amplitude from this part, and this will give you the phase. So at the end of the day, you'll have the wave function, and you sum over all the configuration in the visible layer on sigma with the square root of the Boltzmann distribution on the visible layer after you optimize all the parameters in the hidden. And the phase will give you this S is the phase function here, which allow you to add the complex phase with the wave function. And of course, you sample over all possible configuration in the visible. So this is the wave function at the end.
And in C and E are the same for in each of the S terms. Oh, they're different.
So this is like a regulator, and these will change with the connection. These are the parameters.
Yeah.
So here's the flow of the algorithm. So we initialize the parameters. I mean, what we have, you have biases on the visible, the hidden, the connectivity matrix, the D and F and C and E from the phase. And this is can be started with random distribution, and later we'll show what we call in machine learning like warm start, that if you have a good point in a potential where you change the internuclear distance, you start from that value instead of going back to the random initial values of the parameters. And then you construct the amplitude, as I mentioned before, from there. And here, this is where the quantum part. So the quantum part will be a quantum circuit that do the Boltzmann distribution and sample from the Boltzmann distribution to get the wave function. So this is only the quantum part. And then what is the optimization is the cost function is really the expectation value of the Hamiltonian. So you have to minimize it with respect to the parameters in the quantum circuit, in the restricted Boltzmann machine, with respect to all these parameters. So if there is convergent, you continue. If not, you go and update the parameters and continue with the iteration. So let me go through a couple of notation here so you can see when I talk about the scaling and the implementation. So now each node in the visible node is mapped to 1 qubit in the circuit. So we have n visible neurons, we have n visible qubits. And when we do the electronic structure calculation, this is the number of spin orbitals that we are using to do the calculations. And each neuron in the hidden nodes is mapped also to 1 qubit. And again, the values of these is plus minus 1. And if it's plus 1, we call it 0 here. And if it's minus 1, we call it 1, both in the visible and the hidden units. And we have ancilla qubit is n times m for the ancilla qubit. And this is the product is needed really to sample and introduce the connectivity between the two layers, this omega matrix. So here's the quantum circuit for the sampling. So what we have, we initialize all the qubit in the 0 state. We have visible nodes, hidden node, and the ancilla qubit. And here, when we talk about the number of qubits here or the scaling, I mean, the problem that we are solving, we solve it with 2 nodes, 2 qubits in the visible, 2 qubits in the hidden, and then we have those 4, the ancilla qubit. So the way we do with the sampling, we start with the rotation, where the angle of rotation depends on the biases on these biases on the visible. And you can see the 2x2 matrix here for rotation. And we do rotation on the hidden with the angle that related to the biases in the hidden node. And the idea is to make superposition of all possible configuration. So this is the relation between the rotational angle here and the biases, both in the visible and the hidden units. And now so this is, if you sample up to this point here, you see you get the amplitude, which is the square root. I mean, the wave function is the square root of the amplitude over the visible layer. Now let's continue and add the ancilla qubit here. So now the ancilla qubit is, you have to connect the rotational angle here, and you do control rotation. So this rotational angle here depends on the matrix element which connect the 2 layers. And we show in the paper the details how this is done and why this are the right rotational angles to connect. So you can see control from the visible, hidden, and then the ancilla qubit here. And for example, the control here, we decompose it when we did the implementation with the X gate. And you can see here you need 6 Qiskits to decompose this control rotation. So once you do this quantum circuit and you do the measurement in all the qubits, when it collapses to 1, and I will show you this one here, you have a successful sampling. And we show that the probability or the success probability of getting 1 in the ancilla qubit when you do the measurement, there is a lower bound, which is at the end, it's given by 1 over, this is, and just like to mention that we introduced the K parameter, which you can think about it as a effective temperature. And not sure if we have it here, but yeah, this is, sorry. We introduce a parameter here in the distribution, and we optimize this parameter, which allow us really to get a lower bound on the successful sampling. And we show that if you choose K of this form, you have a constant lower bound, which goes like e to the -4, which is around 10 to the -2. And in the paper, you can see the exact analysis, how to get this inequality and get the scaling to e to the minus. So I see, let me just get this one and get to the results because we are really running late. So as I mentioned, for these applications, the matrices were mainly 4x4 to prove the concept for these materials. And we needed 2 qubit in the visible, 2 qubit in the hidden nodes, and 4 ancilla qubits. And when we count the rotational gate, we have 4 single qubit rotational gate from n plus m. We have 4 control rotational gates. But once you decompose it with the x, so you have 6 times n times m. So this is why the scaling goes like in the quadratic with number of qubits. So if the density is like n over m is 1, so you can see this goes like n squared. And when we do the implementation, the number of iteration was around 30,000 in the quantum simulator, and on the real machine, 500. And we run this calculation on Qiskit, the students run it on Qiskit, and the IBM quantum machine with the 27 qubit, both Cindy and Toronto. So again, I don't want to go through this one. The scaling is, I said here, quadratic for the sampling, and of course, it's exponential when you do classical sampling. And the cost function is optimizing the expectation value of the Hamiltonian once you get the ground state. For the ground state, you get 1, and we show also you can get it for excited states. So you have to optimize this one with respect to all the parameters in the restricted Boltzmann machine. So first, in the natural communication, we show how the method works very well for simple system like H2, lithium hydride, and so on. And you can see clearly here the number of nodes. We started with 4 and m, 4 and 8 for this simple system. And for water, we have 6 qubits, and m was 6. And then we analyze the density, like if you change the number of hidden units compared with the number in the visible units, and we show the conversions. Even if you, like here, we go from 4 to 6, and we say still the conversions within the chemical accuracy. And then the next move was really to get this one, because in the early work we did this one only real to get the side of the wave function. But in order to get the phase, you need this one to be complex. And the extension to complex phase was done first by the Japanese group, and they published their paper in 2021 based on our earlier work. And what we did, we implemented the quantum circuit with this one on the Qiskit and the IBM machine. And we didn't run the simulation for the hexagonal boron nitride and graphene, again with 4 qubits. And the results were really excellent when you compare it with the exact diagonalization, both for the cousin simulation and when we did with the IBM quantum machine, we add here two things. We have error mitigation from measurements and what we call the warm startup. We start a point where once we have convergence, we use it to move along this momentum space. Because if you start at each point randomly, the results will be all over the space. But if we use what we call warm, initializing in a warm fashion, which means you use the earlier point, which you have convergence to get the next point, get excellent results, and all the results within a milli electron volts accuracy. And the details you can find it in this paper. And here I would like to move to the excited states, because what we did before was looking at the ground state, but also we can do excited states using this cost function, where we have this one for the ground state. If there's no external, I mean, this is the penalty. If this was one not there, this is what we did before. But we can add a penalty and use what our knowledge, how to get excited state if you know the ground state, because the excited state must be orthogonal to the ground state. So once we do the calculation for the ground state, we use it to really build the excited state with this penalty condition here. And of course, you need this one. This is the operator for that you would like to use in this penalty function. And this is the eigenvalue of this operator. And we square it to get it a positive number here. And Dr. Maras, who's a postdoc in the group, used it successfully to simulate two-dimensional material, molybdenum disulfide and tungsten disulfide. And I will not mention here the detail of the Hamiltonian for this system. It can be found in this reference, where they start with density function theory and they build the Hamiltonian. I'm not talking about the Hamiltonian, but the Hamiltonian we used is a tight binding Hamiltonian for this system, and people optimize the parameter using DFT and other techniques. And here is the tight binding Hamiltonian. We have hopping to the third nearest neighbor. And there is an approximation what kind of orbital to use to describe the valence and conduction band. And they use 3 orbitals. And this is, you talk about the metal here, the DZ orbitals, and XY and X squared minus Y squared. So you have three orbitals, and our Hamiltonian is 4 by 4. And again, we use the same number of qubits as we did before for graphene and hexagonal boron. It's the same quantum circuit, but the parameters are different for this one. And here we choose this operator to be in the ground state, and omega depends 0, and the penalty parameter to be larger than the norm of the Hamiltonian matrix. And since we're running out of time here, I will just show how powerful is this restricted Boltzmann machine in getting both the valence and the conduction band. And here you see comparison between exact diagonalization, which is the solid line, and you have the restrictable machine. When we talk about the classical, we're using our classical computer, and then QASM and the IBM Q machine, the quantum machine, with error mitigation and warm initiation the point. And you can see the accuracy with the 3 different methods here. And when you look at analyze the errors in the energy in the electron volt, you see that it's in then 10 to the minus 6 for the conduction band. And you see in the valence, it's the same, it's very, very accurate number. And when we examine the infidelity is related to the overlap with the wave function coming out of this restricted Boltzmann machine with the exact wave function, absolute value square. And you take 1 minus, and you see extremely good results compared with the exact, or here we talk about the overlap with the exact wave function with error to the minus 10 to the minus 5, 10 to the minus 6, both in the conduction band and the valence band. So I will not get into this one, but people asking, okay, what is the importance of this material? I just would like to mention that now we have an ongoing collaboration with the people from the ECE, and for those two materials, we have shown last year that these materials can be used to build what we call quantum coherence and bright and dark bands, and increase the efficiency of solar cell beyond the classical or the Shockley-Quasar limit, which is around 33%. And this is where you have a quantum coherence coming out of the coupling, the double coupling, and the donor layer here. And for those who are interested, I mean, we just put together this material and was published in Advanced Functional Material last year, showing how this material is extremely important in getting the efficiency of solar cell beyond what we have all the time, which is 33% coming out of the Shockley-Quasar limit. So here I will, instead of describing, maybe I'll just choose one new direction, and briefly I go through what we are trying to do in the group using restricted Boltzmann machine. And we're trying to push it in many different directions. Like the work of Manas is really trying to see how one can engineer, do band gap engineering for these materials. Look at spin orbit coupling. Once you know the Hamiltonian for spin orbit coupling, and he has initial results showing that also spin orbit coupling can be implemented, and you get results both on QASM and IBM quantum machine. We show how finite size scaling can be done on this quantum machine, and combining restricted Boltzmann machine with the renormalization group, trying to understand the physics. Why this machine works so well? I mean, there are two things. I mean, you can use it as a numerical apparatus to get results, which we saw that this is really excellent as a proof of concept comparing with the exact diagonalization, but at the same time, you'd like to understand why it works. And we have a couple of ideas to see how we relate it to renormalization group techniques, where the idea here, you reduce the dimensionality of space, you come up with an effective Hamiltonian for the low-lying states, and maybe this will give us like a physical intuition, trying to understand why this restricted Boltzmann machine works very well. So here I'd like just to point out that with our earlier work, we found a mapping between the thermodynamic limit and the size of Hilbert space. And we talk about phase transition in Hilbert space. Hilbert space is infinite. So if you start with a basis set finite, you get finite results. And then, I mean, you can extrapolate it. We have a formalism how to extrapolate information in the Hilbert space and get the criticality. And this was a very successful way of getting the criticality in when you break the symmetry of electronic structure configurations. And we done this work almost 20 years ago with the early work of my two postdocs, Juan Pablo Nairoti, who was in the math department at Aston University in England, and Pablo Sierra was a professor of physics at Cordoba. And we published the results about 20 years ago, showing how you can do finite size scaling in Hilbert space. And now we're doing quantum phase transition in qubit space, because we have this mapping between the number of base function and number of qubits. So we do this, for example, to analyze recent experiment in the quantum Rabi model. The quantum Rabi model, you have you can think about it as one two-level system as a qubit interacting with bosonic field. And you can see here, this is the paper in Physical Review Letter about the analytical solution. And then the Chinese group did an experiment showing this phase transition. Although you have a finite system, only two-level system with external feed. And we can get the same results using our finite size scaling. And here the students, Bilal, Khalid from the physics department, show how one can use finite size scaling in Hilbert space to get this criticality. And Srihari from the electrical computer engineering ran it on QASM. And he showed that also in if you map it to the qubit space and use the restricted Boltzmann machine with the same techniques we talked before about getting valence and band structure, you do it here for this system, and you can see the criticality in the qubit space. And here I'll just mention the work that we are doing now with the students, Raja and the postdoc, Sangshul, trying to analyze or understand the relationship and how to understand the success of restricted Boltzmann machine in getting the spectrum of this molecular system, comparing with the work in renormalization group, and how deep learning is really related to the flow and RG approach. And then with Andrew, we were trying to see how one can look at the relationship between running the quantum master equation, where you have the noise in the system or the environment on a quantum computer, and the idea here again to increase the space, what we call the Krauss operator. You increase, because this is the nonlinear part, so you increase it to make it linear, and you run it on a quantum computer. And the question is how to couple this with the restricted Boltzmann machine and get more efficient calculation for the open system. And here I would like just also take a few minutes to mention what we do in the quantum state classification. And sorry, I'm going fast, but all these problems, I mean, you can see in you can look at our archive paper. I mean, you can see more details about the project, and I would just like to mention it. So you can see where we are pushing with this restricted Boltzmann machine in different areas of research. And the graduate student, Zhang Shuli and Rishab and Summit are pushing the restricted Boltzmann machine in state classification and tomography. And just the last project with collaboration with the engineering department here at Purdue, with the joint student, Blackie Wilson, who is looking at really inverse design and engineering problem using quantum sampling. And he put his paper on the archive. So let me just summarize. So please, I will get another few minutes to summarize and then stop for questions. So just to summarize, we showed that restricted Boltzmann machine with 2 layers and 1 for the node can accurately give you the whole spectrum, not only the ground state and excited states. And we show how it works for simple molecular system and 2D materials, where you introduce periodic boundary condition, which request, this is why you need the phase of the wave function, and this is why the complex phase in the nonlinear activation function. We show the scaling goes quadratic with the resources for the circuit width and depth and the parameter count. We show the successful sampling has a lower bound. We show that this method also can be pushed into a quantum criticality in the Hilbert space, not only on the thermodynamic limit where you have a finite system. And we apply it on our classical machine, on also in Qiskit and IPM quantum machine with error correction, with the error mitigation and warm initialization of the points. And again, the results are within the chemical accuracy. So again, I will just again really thank all. We have all these students working hard in pushing these ideas into new different directions. Over the year, I mean, the last few years, we collaborated, and this is a active collaboration with people, Dudley Hirschbach, Brina Narag at Harvard, Rafi Levine at UCLA, and Fritz Haber, Jerusalem, David Mazotti at Chicago, Young Chen at Purdue, Fritzlav and Fritz Haber, Berlin, and Ruth Bachelor at Air Force, and Travis at the Oak Ridge National Lab. And for funding, we really enjoy the funding. And recently we have funding from the Department of Energy. And this was just 2 weeks ago, was announced with 73 millions was put in quantum information science. With NSF, we have regular funding. And also we were lucky with Yale to have a phase 1 NSF Center for Quantum Dynamics. And this is really exciting because our first CCI center was back in 2010. We were not successful at that time to get phase 2, but now with the Yale group, Victor Batista, Michel Devort at Yale, and myself at Purdue, Eaton at University of Michigan, and Leah Santos at Yeshiva, we get the phase 1 from NSF. And we have funding from here from Purdue Discovery Park And it's really exciting to be part of the new center at Oak Ridge National Lab, the Quantum Science Center. And our focus on this center is in quantum machine learning for quantum materials and topological materials, which I did not talk about it here, but this is really exciting, a new direction. And this is where the focus of this DOE new center, which is one of the 5 centers in the country. And we got also funding from the Air Force. And I would like just to mention that recently we got the okay to go for a planning center here at Purdue, which is a Center for Quantum Technology. This will be a collaboration with us at Purdue and IU in Bloomington and IUPUI in Indianapolis and Notre Dame, for all these 4 schools in Indiana, to connect university research with the industry. And I would like to thank you all for listening, and sorry for pushing this for a few minutes beyond the time. And thanks, Zlatko, and thank IBM for giving us this information, this opportunity to present our research to the people tuning from all over the world. So thank you all.
Thank you very much, Sabre, and thank you, folks. Feel free to post any final questions in the chat as we near the end here. I think some of the questions are getting answered by other people in the chat, so that's really nice to see. Thank you for that. Maybe a few of them also, have you thought about, or what do you think about reinforcement learning methods for some of these problems in the future?
Yeah, I think reinforcement for us is really related to what we do, because what is the enforcement here? We minimize the energy. So you can think about what we are really doing is the reinforcement also approach, because at the end, we minimize the expectation value of the Hamiltonian. So I think for this problem, I will see that our approach is also fit in this category.
Mm-hmm. And I think there was a question, but maybe somebody clarified that the learning here was unsupervised, so there was no prior training.
No prior training, because we started with the initialize all the qubit in the 0 state, and we ran the quantum circuit to really sample, and we sampled from the Boltzmann distribution to get the wave function. So there is no prior like a distribution, and I know it's different from like a state classification where you look at KL divergence, comparing your probability with the given training probability. Here, no, we don't have this training. We minimize the expectation value of the Hamiltonian, which is our cost function. And this is where I thought we are adding the word learning, maybe because of we learn about the right distribution by minimizing the energy or getting the ground state or the excited states.
And how well, or how, like, what are some of the challenges in finding, say, the first excited state with this orthogonality constraint? Is that fickle in some way, or, you know, how does that actually work?
Yeah, I mean, first of all, you have to get the ground state. And since we're already doing this formalism to get the ground state, then you have to choose your parameter lambda, which is the penalty, large enough to optimize the new cost function. So, I mean, the difficulty we're having and this is why we use really the warm start. When we get results which converge for 1 point, this was the excellent way really to move on the potential energy or on the momentum space. But I think it's a variational, so you have to try. I mean, it's like a trial and error to see if you have convergence under the penalty constant for that functional that you optimize. It's like, I mean, the difficulty in any is exactly the same as we do in any variational calculations, and this is also done in a classical computer, just to make sure. The quantum computers, the quantum part is only sampling the Gibbs distribution. So when you do it classically, and this is go back to the calculation of the optimization from variational calculation as we do all the time in different methods.
I think you showed some data for, we went a little fast past this point for the tungsten diselenite, and I think I lost track of how many qubits you needed to use to simulate that.
Yeah, so the Hamiltonian is Hamiltonian is 4 by 4. So we use 2 for the visible, 2 for the hidden, and then we have 4 and set a qubit. So it's like a 2, so you have a 4 and 8.
4 and 8, got it. Do you have do you need a phase one here as well?
Oh yeah, for the 2D materials, we use a tight binding Hamiltonian, which include the boundary condition, and people you take the raising and lowering operators in the second quantization and the do Fourier transform. So you can see in the Hamiltonian, you already build the boundary condition and comes as e to the I k, which is the wave vector times r. So you always have an exponential part has to be simulated. And this is where the difference between the real wave function that we had before and the complex wave function, which force us to add the complex or the imaginary part in the activation function. So really to get the boundary condition in the Hamiltonian, you need the complex phase.
In the earlier slides you showed, didn't the complex phase factor out globally in that C and E?
Yes. Yeah, so this is done. Yeah, this is, yes, it's like maybe I will. Yeah, so this is maybe the wave function. Yeah, this is done in a classical computer. Yeah, it's factor. Yeah, factor out of the wave function. Are you talking about earlier on the slide or?
Yeah, I think maybe we passed. It was in the, I think it was the S or the
Yeah.
sigma. Yeah, the S of.
Let's see if here. Maybe what is the wave function?
Maybe if you just help explain again for us the phase node. Yes, the phase node is.
Let's see. Oh, this
Yeah.
one. This one you mean? Yeah.
Right.
Yeah. So this part is you sample the Gibbs distribution to get the probability distribution, and here for the square root will be for the amplitude.
Mm-hmm.
So now the question is how to get the phase. So the phase, use this tangent hyperbolic function, which allow you to calculate this S. And S is really connected with the visible layer. So this is the phase. So we start with amplitude, which is the square root of the probability distribution. And you include the phase, which is this complex function comes here, and then sum of all possible configurations.
And why do you need C and E inside the phase? Don't they just factor out into a global phase, which then wouldn't be essential in this?
This one we call the regulator. I mean, this parameter is like a constant. So you can shift it back and forth because this is all where the connection with the visible and the hidden layer. And this is like a shift where when we optimize it, will help us in getting the right phase. So it's like we call this is like a regulator. And these are where the connection has to be changed when you do the connection with the visible layer.
Right. So okay, so you want to get the right global phase.
Yes.
Let's see, I'm reading the question. Does your sampling method also work for deep RBM?
You mean more than 2 layers? I mean, we tried only 2 layers. You mean adding more hidden layers? We did not try like this one, but I think it will be interesting to see if we'll increase the hidden layers. We did not try it.
Gotcha.
So
I see.
we have only 1 layer, so they would like to have more than 1 layer. We did not have it more than 1 layer. Is this the question or?
I think so. And Nicholas, feel free to clarify in the chat. Good. And I can see Manas is helping answer some, so thank you as well. Great. I think if I missed your question, feel free to post it now. Otherwise, we're almost 20 minutes over, so we probably should wrap up soon.
Yeah, maybe let me mention here is also the email, just if someone still has questions or would like to get more.
There was one other question that popped up a few times. It was about the slides are very rich with information. Are they available on your website somewhere?
No, but we can post it in the website, and we have other other talks. But I mean, I can also put this one on the website. Yeah, we'll do it. Yes.
Great. Okay, I think we've had a lot of questions and discussion, and maybe before we wrap up, I just leave the stage open to you to share any thoughts or ideas you may want to tie us off with.
No, I think it's really an exciting time because I see here at Purdue, I teach in quantum information quantum computing. And when I taught this class like a long time ago, I have only a few students. And now, every time we open this class for students, and mainly we see large number of students from electrical computer engineering joining the field. So really, this is exciting time. And I see so many young students here at Purdue really trying to enter the field. And in my group, we were lucky all the years to have students from physics, computer science. And now we're having more and more students from electrical computer engineering with different backgrounds. And this is really an exciting time for young people to get into the field. There's so many groups really focusing on quantum information, quantum computing for chemistry problems all over the country and in the world. And really, this is an exciting time to get and contribute to the field. And you see all the results are really in the proof of concept, like a 4x4 Hamiltonians or these simple system. And we need a lot of ideas or young people to come up with exciting ideas how to scale it for large systems. And now since the hardware is I mean, we see the IBM platform having more qubit and then increasing the coherence time. The question is, how do you push these proof of concept and simple ideas into larger systems? So anyway, I will end that. This is really an exciting time for young people to get into the field.
Thank you for the very positive and optimistic outlook. I couldn't agree more, Sabri. And maybe one final question we'll sneak in there as a follow-up. Will the number of qubits also increase with the number of layers as you go to deeper restricted
Yes.
Boltzmann machines?
Yeah, and also increase when we go for larger system, because what I mentioned before, the visible layer, the number of qubits there depends on the spin orbitals that you are using. So we use very simple system like 4x4, so you have 2 qubits in the visible, but if you have a larger system, also this will increase there too. So I mean, we have to come up with ideas how to reduce that scaling too. So it's not only in deep learning. I mean, if the same system with larger molecular system, also the number of visible qubit will increase.
Got it. Well, thank you very much for all the questions and for the wonderful talk. This talk will stay live on the Qiskit YouTube channel. So folks, you can go back and rewatch it or tune into any particulars. I understand the slides will be posted on your website. And I think with that, I'd like to thank you very much, Sabri, for the wonderful talk. And also thank you very much, folks, for tuning in. We will see you next Friday at noon Eastern Time. Have a great day.
Yeah, thank you, Zlatko, and everybody. Thank you.
Thank you.